What if I told you that our entire modern picture of the universe, of space, time, reality itself, all started with a single thought? One physicist had what he called his happiest thought, and that one little spark set off a revolution. So how did one simple idea completely unravel everything we thought we know about the cosmos? Well, let's dive in. So this was it. This was Albert Einstein's big moment. And honestly, it sounds almost simple, doesn't it? The feeling of gravity holding you to the floor is exactly the same as the feeling of a rocket pushing you up from below. If you were stuck in a sealed box with no windows, you'd have no way to tell the difference. That's it. That's the thought.
But this is where the real genius kicks in. See, for most of us, that's just a neat little observation. But if you're Einstein, you don't just stop there. You ask, okay, but what does that mean? How on earth could this simple, perfect equivalence between gravity and acceleration lead to a whole new vision of the universe?
Well, Einstein started thinking, if gravity feels exactly like acceleration for everything, then maybe it isn't a force in the way we usually think about them. I mean, think about a magnet. It pulls on metal, but not on wood. But gravity, it gets everything. You, me, a feather, a planet, we all fall in exactly the same way. So that suggested to him that gravity wasn't some mysterious force acting through space. And this is just a gigantic leap. He basically took centuries of physics, everything since Isaac Newton, and decided to just throw it out. He said, forget about gravity being a pull. It's not a force reaching out and grabbing things. So if it's not a force, then what in the world is it? And here's the answer, and it is absolutely beautiful. Gravity is just the curvature of space and time. Big things like the sun don't pull the Earth. They literally bend the four-dimensional fabric of the universe around them, and planets, well, they're just following those curves. The Earth isn't pulling you down right now. It has warped the space-time you're in, and you're simply rolling downhill. Okay, so this idea is already pretty wild. But what happens if you take it to its absolute most ridiculous extreme? If you can bend space-time, what happens when you bend it so much that it breaks? You get a black hole. And the key thing to understand here is that a black hole isn't really an object. It's a place, a destination. It's a one-way door in the universe. Once you cross its boundary, the event horizon, the very shape of space-time means all paths lead inwards. To get out, you'd have to go faster than light. And that's the one speed limit the universe absolutely enforces. And this is where things get truly bizarre, because reality itself seems to split in two. If you're watching safely from a distance, you'd see your friend fall toward the black hole, but they'd get slower and slower and seem to freeze right at the edge, fading away forever. You'd never, ever see them cross. But for them, they wouldn't notice a thing. They'd sail right across the event horizon, only to realize that their entire future has collapsed into one single point ahead of them, the singularity. For them, it's all over in a flash. So, Einstein's theory, it's incredible. It works perfectly for planets and stars and galaxies. But there's a problem. It doesn't know how to handle the tiny, weird world of quantum mechanics. And when you try to apply the rules of quantum physics to the edge of a black hole, well, everything breaks. A paradox so deep it's threatening to tear physics apart. And then, in the 1970s, Stephen Hawking comes along and just blows the whole thing wide open. He did the math, combining quantum mechanics with the physics of black holes, and found something no one expected. Black holes aren't completely black. They have a faint glow, a trickle of radiation. And what that means is that they're slowly losing energy, shrinking, and over truly mind-boggling amounts of time, they will eventually just evaporate. Poof, gone. Okay, so let's walk through this, because this is the big one, the information loss paradox. You take a book with all the information in its pages, and you throw it into a black hole. That information is now locked away. But we now know the black hole slowly evaporates. So when it's completely gone, what happened to the information that made up the book? See, a core rule of quantum mechanics says information can never be destroyed. So which is it? Did the black hole break one of the most fundamental laws of the universe? Or did the information somehow sneak back out? Our two best theories of reality give us completely opposite answers. Now, the search for an answer to this massive paradox has pushed physicists to the absolute brink, and it's led them to what might be the single, strangest, most reality-bending idea ever proposed in science. So here's the clue, and it's hidden in the mathematics of black holes. Normally, if you want to know how much information you can cram into a space, You'd think about its volume, right? A bigger box can hold more stuff. Simple. But for some reason, the maximum information a black hole can hold has nothing to do with its 3D volume. It's all about its 2D surface area, the area of the event horizon. It's as if everything you need to know about what's inside is somehow written on the surface. This incredibly weird property led to something called the holographic principle. And the idea is just what it sounds like. It suggests that maybe all the information that describes a 3D volume of space, like the room you're in right now, could actually be completely described by a theory that lives on the 2D surface surrounding it, like its walls. The 3D world we experience would be a kind of projection, a hologram. So this is where that one happy thought has led us, to this absolutely astonishing question. Could our entire universe, with all of its depth, its stars and galaxies, just be a holographic illusion, an image projected from a distant two-dimensional surface at the edge of the cosmos? That simple idea about gravity didn't just bend space and time. It's now forcing us to ask if the 3 dimensions we call home are even real, pushing us right to the very edge of what we know and what we can even imagine.